Welcome to a deep dive into one of the simplest yet most intuitive algorithms in machine learning, k-nearest neighbors, or KNN. If you've ever wondered how AI classifies data without building a complex internal model, you're in the right place. KNN is often the first classification algorithm many beginners encounter, and for good reason. Its core idea is remarkably straightforward. Imagine you have a new data point, and you want to know what category it belongs to. The KNN algorithm's fundamental principle is to look at its neighbors. It essentially asks, "Tell me who your closest friends are, and I'll tell you who you are." The classification of this new point is determined by the majority class among its k closest existing data points. The k in KNN is a crucial hyperparameter. It represents the number of nearest neighbors that the algorithm considers when making a classification decision. For instance, if k equals 3, the algorithm will look at the 3 closest data points to our new input. If k equals 5, it will consider 5. Choosing the right k is vital. A small k can make the model sensitive to noise, while a large k might smooth out local structures, potentially overlooking important details. One of the defining characteristics of KNN is its non-parametric nature. This term sounds technical, but it simply means that KNN makes no underlying assumptions about the distribution of the data. Many other algorithms, like linear regression or logistic regression, are parametric. They assume your data fits a particular function or distribution. KNN, however, doesn't care if your data is Gaussian, uniform, or something entirely different. This non-parametric flexibility is a significant advantage. It allows KNN to learn complex decision boundaries directly from the data without being constrained by rigid mathematical assumptions. This makes it particularly effective for datasets where the relationships between features and the target variable are nonlinear or highly irregular. You don't need to try and force your data into a predefined mold. The concept of nearest is at the heart of KNN, and it's quantified using distance metrics. To find the k-nearest neighbors, the algorithm needs a way to measure how far one data point is from another. Without these metrics, the idea of proximity would be meaningless, and KNN simply wouldn't work. The most common and intuitively understood distance metric is Euclidean distance. This is the straight-line distance between 2 points in Euclidean space, essentially what you'd measure with a ruler. It calculates the square root of the sum of the squared differences between corresponding coordinates of 2 data points. While Euclidean distance is frequently used, it's not the only option. Other metrics like Manhattan distance, which sums the absolute differences of the coordinates, or Minkowski distance, a generalization of both, can also be employed. The choice of distance metric can significantly impact the algorithm's performance, and is often determined by the nature of your data and the problem you're trying to solve. KNN is also known as a lazy learning algorithm. This term highlights how it approaches the learning process. Unlike eager learning algorithms that build a generalized model during the training phase, KNN defers the learning and computation until a prediction is actually needed. It doesn't construct a function that explicitly maps inputs to outputs. What does this lazy approach mean in practice? It means that during the training phase, KNN essentially just stores the entire training dataset. There's no complex model building or parameter estimation happening up front. When a new query point comes in, the algorithm calculates distances to existing training points on the fly, then finds the k-nearest ones to make a decision. This lazy learning has its trade-offs. On the one hand, KNN is incredibly simple to implement and understand, making it a great baseline model. It also adapts easily to new training data. However, the computational cost during prediction can be high, especially with very large datasets, because it requires scanning through all existing data points for every new classification request. In summary, k-nearest neighbors is a powerful example of a non-parametric, distance-based, and lazy learning algorithm. It classifies new data points by simply looking at the majority class among its closest neighbors. Its simplicity, lack of assumptions about data distribution, and intuitive mechanism make it a foundational algorithm in machine learning, demonstrating that sometimes, the simplest approach can be remarkably effective.